Okay, our next speaker is Nawras Alnaasan, and he will be joined potentially by Horng-Ruey Huang, and they're going to be talking about characterizing the communication in these really large parameter efficient large language models. All right, take it away.
Okay, thank you, Shelby. Good morning, good afternoon, everyone. Um, Thank you for joining this session. My name is Nawras Alnaasan, and along my colleague Horng-Ruey Huang, we're excited to present our recent work on characterizing communication and distributed parameter efficient fine-tuning, also known as PEFT, for large language models. And in this work, we aim to provide valuable insights into the efficacy and practical implications of employing PEFT methods with an overall goal of facilitating the development of scalable approaches for fine-tuning large-scale models. So let's get started. This is the outline of the presentation. We'll start with some background into the fine-tuning and PEFT, and then the motivation behind this work. Then we'll move into challenges and contributions, proposed evaluation, performance numbers, and finally the conclusion. So first, let's briefly cover some background and look at preliminary results. So the pre-training phase of LLMs is often followed by fine-tuning on a downstream task, and this is intended to adapt this general pre-trained model to a specific task or domain by continuing the training on a more specialized data set. However, just like with pre-training, as model and dataset sizes increase, fine-tuning becomes computationally intensive due to the huge volume of parameters involved. This is especially evident when we look at multi-GPU and multi-node scalability numbers. So this figure to the left shows the throughput in tokens per second for training a 1 billion parameter model, GPT-like model, so decoder-based transformer on A100 GPUs. And as we go from 1 to 32 GPUs, we observe that the scaling efficiency is around 81%. To better understand this degradation of performance per GPU, if you look at this figure to the right, we see the breakdown of training. Basically the training iteration time, where we have here blue is the computation time, orange is the communication time, and red is the overlap between the two, communication and computation. And as we go from 4 to 8 GPUs and beyond, we see this sudden jump in communication overhead. This is because in the experimental setup, we have 4 GPUs per node that are connected via NVLink. And as we increase beyond the 4 GPUs, we need inter-node communication via the network, which is significantly slower than intra-node communication. So all of this is with full fine-tuning. But now let's take a look into how parameter efficient fine-tuning is different. So this figure shows a comparison between the weight update for regular fine-tuning or full fine-tuning compared to LoRa, which is probably the most popular PEFT method right now. And here on the left, we see that for the pre-trained weight matrix W, in each training iteration, we compute the entirety of the weight update. And we apply this weight update to the weight matrix, and then we proceed to the next iteration. Now, what LoRa does is that it takes this weight update matrix, delta W, and it decomposes it into two much smaller matrices, A and B. And to just to put this into perspective, the size of A and B combined can be only as small as 1% or less of the actual size of W. Um, but when we multiply A and B, we get a matrix that has the dimensions of W. So this is simple matrix decomposition. And the trick with LoRa or PEFT methods in general is that during training, we freeze all of the original model weights and update only the active LoRa weights. So that doesn't mean that we don't need the old weights, the original weights of the model during the training. We still need them. But the main advantage here is that we see more memory and computational saving due to the reduced gradient calculations. So, and this reduction is about 25%. So we only need to calculate the gradients for the active weights, but we still need to calculate the gradients for the activations. What we save time and resources on is calculating the gradients for the frozen weights. So now we have an understanding of the of PEF methods in general. Why do we study, or why did we study the distributed PEF in this paper? So several previous studies have examined the conversions of different PEF methods. So basically, the accuracy, how does it compare to full fine-tuning? But the performance of distributed PEF methods remains largely unexplored, especially when it comes to the communication overhead and the potential overlap between computation and communication. And scalability, of course, is a major factor to consider when choosing a fine-tuning method, because this can be like a significant investment of time and resources. And in this paper, we strive to lay the groundwork and understanding for more efficient and scalable approaches to fine-tuning large-scale models and in various application domains. So moving on, some of the challenges or questions we try to address are as follows. What is the impact of communication overhead resulting from the distribution of PEF workloads across multiple GPUs and nodes? How does the overlap between computation and communication influence the efficiency of PEF? How do PEF methods perform with different model sizes? How does the scaling compare to full fine-tuning? And what is the impact of mixed precision and quantized training on the performance of distributed PEF? And finally, what are the memory requirements for training with the PEF methods compared to full fine-tuning? When it comes to contributions of this work, we conducted a comprehensive evaluation on a modern GPU system with NVLink and InfiniBand interconnect, utilizing up to 32 NVIDIA A100 GPUs. We study the communication overhead and try to provide an in-depth analysis of the overlap between communication and computation for different PEF methods, like LoRa, Ada LoRa, Aloha, Lockhart, with the baseline being the full fine-tuning. And then we evaluate different model sizes. Again, these are GPT-like open source decoder-based transformer architectures. And then we find that PEF methods yield much better scaling efficiency compared to full fine-tuning. We're going to explain why. We also see significant improvements with mixed precision. So with PEF, we see like up to 90% efficiency when scaling, compared to only 27% for full fine-tuning. And finally, we compare the memory requirements between the two methods. So for evaluation, we define multiple metrics in the paper. We explain them in details, including speed up factor, scaling efficiency, model throughput, training iteration time, pure communication latency, and communication volume. And we use an analytical model to estimate the communication volume. And we compare it against the empirical results. And we see that these two match exactly. So in this study, we focus on distributed data parallelism, DDP. For future work, or actually ongoing work, we are looking at 3D parallelism and FSDP, fully sharded data parallelism for larger model sizes. So this study, the largest model we evaluated is 1 billion, but we are also looking into larger models using these state-of-the-art methods. But briefly, this is the workflow of PEF with DDP. This example shows two GPUs where we have the data set on the file system. We take a batch, we divide it into two mini batches. Each GPU will take part of the data. GPU 0 will have a replica of the model, similar to GPU 1, with most of the model weights frozen. So the majority are frozen, and then only the lower weights are active. For the forward pass, we use all of the weights, so both frozen and active. Based on that, we calculate the loss or the error. And in the backward pass, we calculate the gradients. but the gradients that we care about are only the ones for the active weights. And then on both GPUs, we'll end up with local gradients, so different gradients since each model replica is seeing different data samples. So to synchronize, we do an all reduce operation. We accumulate these local gradients, and then we'll end up with global gradients on both GPUs. Only then we'll do the weight update and then proceed to the next iteration. So the key advantage here and this distributed setting is that the all reduce operation is much cheaper compared to the full fine tuning, since the local gradients here that we care about are only for the active weights, which are again like as low as 1% of the full weight matrix. And then this is the layered architecture of the distributed fine-tuning environment we use. We have the modern HPC system at the lower layer, and then different hardware and communication toolkits and communication libraries like MPI, Nickel, CUDA, Cudian, and we use Torch Distributed and Hugging Face Accelerate as a distributed deep learning middleware. And then the deep learning frameworks that allow this PEFT fine-tuning on LLMs include PyTorch, Hugging Face, and Hugging Face PEFT. And then at the very top, we have the fine-tuning application itself. For profiling, we use the Torch profiler OMB, OSU micro benchmarks for the collective and pure communication profiling, and then TensorBoard. So with that, I will hand it over to Horng-Ruey, who will present the evaluation results. Horng-Ruey?
Yes, I'm here. So next, I will present our experimental result. So we use assess our experience around a sense system and the Ohio State supercomputer centers. So we use the for NVIDIA A100 graphic card with embedding within Node and use NVIDIA 200 gigabytes infinite band interconnect for intranode. And for software package, we use Nickels with Pitch 2 and also use PyTorch and Hugging Face. For model and data sets, we use PyCI model, which is GPT like models with different model size. So we have 160 million, 410 million, and 1 billion. And then for the fine-tuning method, we use LoRa, LoRa, Lockhart, and Lockhart for path method, and we use full fine-tuning method as baseline. We also do some experience for quantized fine-tuning, so we use QLoRa's. Okay, next slide. And first, I will show the experience run on single GPUs. So at the left side, we can see that full fine tuning has the throughput of full fine tuning is lower than the path LoRa and other path methods. So the reason we can see at the right. So at the right there is a breakdown of for the single training iteration. So we can see that in the pie bar the full fine tuning is the total time for the full fine tuning is 2.5 seconds, and the backward pass is the most take the most time for the training iteration, and compared to a full fine tuning, Nawras have lower backward pass. So so this is reason why the full fine tuning will have low throughput. Okay, next slide. Next, we will discuss the experience around multi GPU and multi nodes. So at the left, we can see that the full fine tuning is the scalability of a full fine tuning it's not great. But for LoRa and others, path matter is they have good scalability. For the reason we can look at the right. So for the single node, the communication overlap for the red bar and the orange bar is quite small. The reason is that um the bandwidth for within the node is quite large, but when we increase the number of GPUs, the communication overhead will have a significant increase. Okay, okay, next slide. So so after that, we will discuss the we'll further discuss the training iteration breakdown running on 32 GPUs. So at the left, the full fine tuning span 3.1 seconds, which is longer than the total time of LoRa, which is 1.8 seconds. So in this pie chart, we can see that the communication overhead, which is the red part and the orange part, is larger than, and it is a large percentage compared to LoRa. So so on the right, we can the figure shows the total or reduced latency per training iterations. So first we can see the latency for LoRa is constant from 2 GPU to 32 GPUs, but for full fine tuning, there is a jump from 4 GPU to 8 GPU. The reason is that there is communication overhead. The communication overhead have a significant increase for from intranode communication to internal communication. Okay, next slide. So at here we will discuss the communication volume. So in the table, we can see that the full fine tuning have 50 cores, and each core will have each core of the message size is 77 megabytes. So the total communication volume for full fine tuning is almost 4 gigabytes. But for LoRa and others, path method is below 10 megabytes. So at here, we can see that there's a lot of communication volumes saving at here. And at the right side, this is peer communication performance. So at these figures, we can see that um, as when the number of the GPU is lower than 4, um, um, the communication, the latency is constant because in the previous slide we know that the internal communication overhead is still due to um the the large bandwidth within the nodes, but as we increase the number of GPU up to 8 or above, there's the latency will have yeah has a significant increase because um so we can see that the communication overhead there is a large communication overhead. Okay, next slide.
4 minutes.
Okay, so next I will discuss mixed precision distributed training. So at the left side, we can see that the PEP method have a high peak memory consumption compared to LoRa and others PEP method, and also full fine-tuning has low throughput. And at the right, there's we also can see the full fine-tuning with FP16 and BF16 have a poor scalability due to the communication overhead within for internal. Okay, next slide. So we further have shows the breakdown of single training iterations. So we can see that the communication and overlap for full fine tuning is larger than LoRa's. Okay, next slide. So for we so 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 we compare QLoRa and LoRa's, and we can see that QLoRa has less peak memory and high throughput. And for multi GPUs, the QLoRa shows the port a little the scalability for QLoRa is not great. A little bit. Okay, next slide. So that is a peak memory analysis. We can see that the full fine-tuning method will need more peak memory compared to LoRa. Okay, next slide.
Okay, thank you, Horng-Ruey. So with that, in conclusion, and this work, we examined the communication dynamics involved in PEFT for LLMs. Our study emphasizes the crucial role of communication efficiency and the performance and scalability of PEFT, utilized across GPU clusters. And then the overall conclusion here is that PEFT methods do not only offer computational and memory savings on the single machine, but also um, it is very scalable due to the reasons we just explained. And this knowledge should aid researchers and developers to decide the fine-tuning method that best suits them. So with theft, yes, there is some trade-off in some scenarios when it comes to conversions, but given also the fact that we're saving on computation, on memory, and we're getting very good scalability, this will play a role in deciding which fine-tuning methods to use. And as mentioned before, for ongoing research, we are exploring other parallelization strategies, such as fully sharded data parallelism and 3D parallelism, and how can we optimize these strategies further specifically for the PEFT workloads. So finally, we have a very exciting program at Harai from our research group, the MVAPITCH group at OSU. We have 4 other talks planned, including 2 papers and 2 tutorials on HPC and high performance deep learning. So we look forward to seeing you in all of these talks. Thank you very much for listening, and we are happy to take any questions. Thank you.
Thanks, you guys. Does anybody have any questions? Yeah, it looks like we already have one in the chat. Kuhn asks, can I assume the characteristics of full fine-tuning baseline presented is going to be similar for the pre-training characteristics?
Yes. So full fine-tuning compared to pre-training, the computational aspect is exactly the same. So both communication and computation will be identical.
Awesome. The next question is from Pankaj. Part of the backward pass is recalculation of gradients. Was that more pronounced for large models and low memory?
Could you Pankaj, can you elaborate more on the question? Oh, recalculation of activations. Okay, so you're talking about activation checkpointing. So for this study, since the models that we're using do fit in the memory of a single GPU, activation checkpointing was not required. However, in the ongoing research that we're conducting, yes, we are using activation checkpointing, and it is necessary for, at least it is the state of the practice for LLM training and fine-tuning. But yeah, at this point, we do not have any results to show on that front. But thank you for the question.
So Kuhn asked, the amount of time reduced for backward pass seemed like 2x using LoRa, which isn't as low as 1% of weights being activated. How do they correlate?
Yes, that is a very good point. So in fact, the time saved and the backward pass is around 25%. So it's not 2x. The reason for that is like during the forward pass, again, we're gonna use all of the parameters of the like both frozen and active. And the backward pass, to calculate the gradients of the frozen weights, I'm sorry, of the active weights, we need the gradients of the previous activations, right? So this is back propagation, right? It should propagate from the last layer to the first layer. And in doing so, we'll need to calculate partial gradients along the way. So when we say it's only 1%, that does not mean we're only calculating gradients for this 1%, right? We care about only the 1% for updating the weights, but in the process, we're going to calculate a lot of other gradients that are unrelated.
Okay, awesome. I think with that, we should conclude because we need to get on to our keynote, which starts in a minute. But thank you so much, Nawras and Horng-Ruey and Wei Yang for the first talk. Happy conference, everyone.
Very good. Thank you, Shelby.